Hello everyone and welcome back. Now in this lecture we're going to start a sequence of lectures that focuses on second order differential equations. Now you know this terminology based on what we talked about in the second lecture. A second order differential equation has a second derivative in it. So we can write these in the following form. So now it looks a lot like those first order equations that we've been focusing on, but you can see the added derivative or first derivative term in the right-hand side, and the left-hand side is entirely our second derivative. Now, other than just looking a little bit different than what we might be used to with the first order equations, these solutions to these equations behave very, very differently than those to the first order equations. And that's what we're going to explore over the sequence of this lecture series that follows. Now, the first thing that I would like to point out is that we're going to focus primarily, at least to get us off the ground, on homogeneous first order linear equations, second order equations. So they are going to take this form. Y is equal to, say, g of t. Okay, so this is very, very similar to what we saw with the first order linear ordinary differential equations. There was no q and there was no second order derivative here. Basically the same idea. And we say that if g of t is equal to 0, then we call this homogeneous. And if g is not equal to 0, this is called inhomogeneous. Now, what I'm going to focus on for the duration of this lecture is working with homogeneous equations where p and q are constant functions. Okay, so this is just the first introduction that you're going to get to second order differential equations. And let me start with an example. Let's talk this one through. And this is going to really set up how I want to approach some of the following lectures. So here's my second order equation, okay? Y double prime minus y is equal to 0. And something that we'll see as we sort of move through this lecture series, I want to make this an initial value problem. So I give you an initial condition here. But what we're going to see is that for these second order equations, I need two initial conditions. So I need an initial condition on the state, and I need an initial condition on the derivative. So this is, right off the bat, the first difference between first order equations and second order equations. Now, you can keep a sort of general rule in mind as you move through these things. Whatever the order of the differential equation is, that's how many initial conditions you're going to need. So for example, if you have a third order differential equation, you're going to need an initial condition on the function, its derivative, and its second derivative. That's 3 initial conditions. That's exactly what we're seeing here. Second order, you need an initial condition on the function and on its derivative. And we're going to see sort of where this comes through as we work through the examples, but I just want to highlight that right here. Now, I'm not going to show you how to solve this right off the bat. You can probably look at that equation. You can tell me, hopefully, what solutions actually work in this thing. So, in fact, both e to the t and e to the minus t are solutions. Okay, so this is now another interesting piece of second order differential equations. I not only have 2 initial conditions, but I actually have 2 solutions. There are 2 different functions that satisfy this differential equation. Now, what I want you to notice is that if I put a constant in front of either one of these, in the same way that when we think about the first order equations, it's always something like c e to the some power, maybe e to the t. And we use that c to fit to the initial conditions. Well, if you pause the video for a moment and you sit down and scribble on a piece of paper next to you, if I put a c in front of either one of these functions and I try and make it satisfy both of those initial conditions, you're going to see it's not going to work, right? And this is something that we learned in linear algebra. If you have two conditions that you have to meet, you need two equations to meet those conditions. So only having one unknown, so some constant in front of these things, is not going to be enough to drill down something that fits both of these initial conditions unless we get very, very lucky. So the question is, what do? Do we just sit back and say, well, maybe there is no solution. Maybe there's no solution that actually goes to those points. That's a possibility, right? I haven't told you that there is guaranteed to be a solution. But what I want you to notice is that this is a linear differential equation. And linear differential equations have a really nice property that I can add up solutions and still get a solution. So I can actually define a general solution to this ordinary differential equation. And it comes from a sort of superposition of both of these solutions that I just found. So in fact, I can write y of t equal to a constant multiple of the first one that I found, e to the t, plus a constant multiple of the second one that I found, e to the minus t. Now what I want you to notice is that that general solution for any value of c1 and c2 is still going to satisfy the differential equation. Go ahead, pause the video, work out the calculations. Double check that this is in fact a solution to that differential equation. Or if you don't want to do that, you can believe me here, and what I want you to notice is that now I've got two unknowns. I have constant 1, c1, and constant 2, c2. That's very good for me though, because I have two conditions that I need to fit here. So now we can play a similar game to what we did with first order equations, and we can determine the value of c1 and c2 that fits these conditions. So what are they? Well, the first one, y of 0 is equal to 2. That's my first initial condition. Well, and when I put 0 into these equations, here I get 2, that's y of 0, which is equal to c1 times 1, so c1, plus c2 times 1. Okay. Similarly, I've got y prime of 0 is equal to minus 1, which, same thing, I've got to take a derivative of this. That's pretty easy. We can definitely do that. The only thing that's going to change is the derivative puts a minus sign in here. And now that means that I get c1 minus c2 after evaluating at t equal to 0. Now this might be bringing back traumatic memories from linear algebra, right? Because now I have a linear system of equations. I have two unknowns, c1 and c2. I have two equations that can be used to solve for these things. You can use any method that you like. You can use back substitution. You can use row reduction. You can invert matrices. They all will give you the right answer as long as you do this correctly. And in fact, you solve it in whichever way you want. You can find that c1 has to equal to 1/2, and c2 is equal to 3/2. But this is very, very nice because now I've got a solution to my differential equation. So y of t is equal to 1/2 e to the t plus 3/2 e to the minus t. That is the solution to my differential equation right there. Okay, so maybe you're thinking to yourself, Jason, that was nice, that's interesting, right? But really, everything that you just did relied on this step right here. And that step was you looking at the differential equation saying, I know what the answers are. Unfortunately, Jason, I'm not that skilled, or I haven't gotten that good, or I haven't practiced enough to be able to do that. So how can I actually do this in practice, right? Because this is the crucial step. I need to identify what these two solutions are to get my general solution, and then I can use those to solve. Well, luckily, there is a general procedure at work here, and let me show you what it is. So let's say generally. Okay, so imagine you're given an ordinary differential equation, a second order equation that looks like this. So let's say a times y double prime plus b times y prime plus c times y is equal to 0. Where in this case, a, b, and c are all constants. So I'm looking at a very, very specific case of second order linear equations, which again is a very, very specific case of just second order equations. But let's start with this, right? We have to start somewhere. Well, here's what we're going to do. We're going to substitute exponential functions. So let's set y is equal to e to the RT. Okay, so r in this case is currently unknown, but I'm going to make an assumption. I'm going to say I think that all of my solutions to this differential equation should be exponential functions. Now, this is a massive logical leap that you will see actually ends up working, but the idea to do this is not immediately obvious. So if you're wondering where this comes from a slightly more advanced mathematics where we can say that all of the solutions take this exponential form. But for now, just bear with me, okay? Give me a little bit of the benefit of the doubt, and let's assume that the function y is equal to e to the RT. Well, first of all, if we're going to substitute it in, I'm going to get r e to the RT for the derivative, and I'm going to get r squared e to the RT for the second derivative. So that means that when I toss this into my differential equation, this gives me a r squared plus br plus c all multiplied by e to the RT. Now, e to the RT is always positive. And so that means that if this thing is going to equal to 0, r has to be a root of this quadratic equation. So really, ar squared plus br plus c has to equal to 0. And what you need to do now is potentially use the quadratic formula in order to determine the values of r. Now, this equation right here is called the characteristic equation. Okay, so we call this the characteristic equation of this ordinary differential equation. And what we get is that if we have, say, two real roots, which I'm going to call r1 and r2, then we have solutions. So we have solutions to the differential equation given by e to the r1 times t. Remember, we assumed that the solution to the differential equation was e to the RT. Now I identified one of the values that actually makes this 0, the characteristic equation. So that gives me a solution e to the RT. And I've got another one, e to the R2t. And so, therefore, generally, I get a general solution. So I get a general solution, which is given by y of t is equal to c1 e to the r1t plus c2 e to the r2t. Now, let me just pause for a second and do a little bit of mind reading, right? You are thinking something very, very important. You are thinking, well, Jason, I have spent a lot of time with quadratic equations, and I know that it is not always the case that you have two real roots. And I completely agree with you. That is very rarely the case, in fact. So how do we handle those cases when you might have complex roots or you might have a double root? Well, that will be the subject of some lectures that will be coming up in this series. So in this one, this lecture right now, I'm just giving you the absolute basics. I want to get you fluent with second order differential equations, and I just want you to see how we can handle this case where you have two real roots for the characteristic equation. Okay? So we will address the more general cases as we move through this lecture series, but this is the case that I'm focusing on here. All right. let's do an example. I've already given you one example right here. We saw that the roots were 1 and minus 1. That's because the characteristic equation associated to this ordinary differential equation, well, a is equal to 1, b is equal to 0, and c is equal to minus 1. So the characteristic equation is r squared minus 1 is equal to 0, which has solutions r equal to plus 1 and r equal to minus 1. R equal to plus 1, r equal to minus 1. So everything is sort of working out here, right? So it's not that I just had a lucky guess here. It's because I could actually do the work to back it up. I could find the characteristic equation and I can solve for those roots. Okay, so let's do another example. Let's look at y double prime plus 5y prime plus 6y is equal to 0. And here's the conditions I want to give you for this thing. Y of 0 is equal to 2. And y prime of 0, remember I need two initial conditions. Y prime of 0 is equal to 3. Now here's the beauty of what we have. I can skip a lot of steps, right? Because now all I need to do is identify A, B, and C. And this produces the characteristic equation. I don't have to reinvent the wheel every time I work through this thing. I can now jump and I can say, okay, well, what's the characteristic equation? Well, the characteristic equation is given by A, which is 1 times r squared, plus B, which is 5 times r, plus C, which in this case is 6, is equal to 0. And now, maybe you forgot about it. I really hope you didn't. But now you're going to put your factoring skills to use, right? In this case, our factors are going to be r plus 2 and r plus 3, which implies that I get two roots at minus 2 and minus 3. So nothing that complicated, right? This started with something that might have intimidated you, a very complex looking differential equation, right? Potentially this is the first time you've ever seen a second order differential equation. And what happened? I turned it into something that you can do very, very easily, right? I turned it into finding the roots of a quadratic polynomial. That is nice and easy. That's relaxing, right? In terms of the things that we've done over the course of this class, this has got to be one of the easiest, or at least one of the things that puts our mind at ease. So now we have a general solution, which is y of t is equal to c1 e to the minus 2t plus c2 e to the minus 3t. And now all that we need to do is use those initial conditions. So I have y of 0 is equal to 2. Well, this gives me, again, putting t equal to 0 into this thing, the left-hand side becomes 2, and the right-hand side becomes c1 plus c2. Okay? Similarly, for y prime of 0 equal to 3, well, putting the derivative, so taking the derivative of this thing, evaluating at 0, the left-hand side becomes 3. The right-hand side is going to be minus 2c1 minus 3c2. Again, I mean, think about the sort of relative ease of this thing. I haven't really had to do much calculus. Technically, I had to take a derivative here. But really, it's solving a quadratic equation and then doing a little bit of linear algebra to find solutions for c1 and c2. So in this case, you can show that c1 is equal to 9 and c2 is equal to minus 7. So you can solve that in whatever way you wish. You can use your favorite method of solving these equations. They all come out, hopefully, to give you the right answer or the same answer. And so therefore, our solution to this differential equation is 9e to the minus 2t minus 7e to the minus 3t. Okay, so there we have it. We did it. We solved our first second-order differential equations. Now, they were linear, and in this particular case where we have constant coefficients, so no p of t, no q of t, and certainly no g of t, we're talking about homogeneous equations. Well, in that case, we can really just boil things down to this characteristic equation that does all the work for us. Now, unfortunately, it's not always going to be this easy. So what we're going to do in the next video is we're going to introduce some of the general concepts of second-order differential equations. In particular, we're going to talk about existence and uniqueness theorems. So when do we have a solution? When is it unique? The types of things that we talked about, the general theory. For first-order systems, we're going to do the same thing here. I'm going to show you why we need, for example, two initial conditions in order to pin down a solution. Now, you saw it through a worked example in these two cases, but is it always the case? Maybe there's some second-order differential equations where we only need one initial condition. The answer to that is negative, but you should be questioning everything as you walk through mathematics.